Okay, let's look at this last problem here. So now we're looking at a pH of a solution made from 50 mils of HCl and 30 mils of sodium fluoride. And so again, we're going to write out a table to keep track of things. So for this, again, we want to convert over to moles. And so the number of moles of NaF that we have there is just going to be the same because we haven't done anything with that. That's how much we're starting with in terms of weak base. In terms of weak acid, we can do that calculation really quickly. It's just the volume times the concentration. So that's 0.005 moles of HCl. Okay, so then we can run through this calculation pretty quickly. At the beginning, so this is the end of the reaction. At the beginning, we have 0.005 moles of HCl, and we have 0.003 moles of NaF. We have no HF, we have no NaCl. At the end of the reaction, I'll have, or what's the change, I guess you want to say, is 0.003 moles of the sodium fluoride. I want to subtract out 0.003 moles from HCl. I'm going to form 0.003 moles of HF. I'm going to form 0.003 moles of sodium chloride, which I don't really care about this at all. Okay, so what do I have left over? Again, this, but we don't really care that much about it. We do form some HF. We have 0 of the sodium fluoride present, and we have 0.002 moles of HCl. So what's going to contribute to the pH? Well, we've got some strong acid there. That's definitely going to contribute to the pH. This is the conjugate acid. It's an acid itself, so that also contributes to the pH, but that is typically negligible if you have strong acid present. So this is the situation where you have excess strong acid. The contributions from the weak acid are negligible. What this means, though, is that our calculation here is very, very easy. So this becomes just a normal strong acid problem. So if our HCl, if the number of moles of HCl we have is 0.002, that means we can approximate our concentration of acid at equilibrium to be 0.002 divided by the total volume, which is 80 times 10 to the minus 3 liters. That's our HCl concentration, which is also our H plus concentration. So what's our pH for this solution? It's just negative log of 0.025. Or 1.6. So each of these neutralization situations, so this is more or less, if you can work through this problem, the titration type problems are very similar, but each of these has its own kind of similar workflow for it. So if you have a pH for a strong acid and a weak base, if in the first situation, I end up where I don't go to complete neutralization, so I don't hit my equivalent point. So I have an excess of weak base present. In this case, I use the Henderson-Hasselbalch equation. Actually, let me just rewrite the 3 scenarios down here. So everything I'm saying here is more or less true for strong bases and weak acids. So if you flip over and look at the corollary, it's still true. You just have to change up some of the problem-solving approaches, but it's more or less the same thing. So one scenario that you can have is, so like let's say you're looking at let's say like, I'm trying to think of like a good way to kind of summarize this, and I'm not coming up with anything. Let's just try and do it this way. So one situation you can have is excess B minus. Another situation you can have is where these two amounts are equal. And the other situation you can have is where this is in excess. So HA is a strong acid, and B minus is a weak base. And so we can have situation A, and maybe A is the wrong way to use here. Let's see, Roman numeral 1 situation, Roman numeral 2 situation, and Roman numeral 3 situation. So in Roman numeral 1, we have excess weak base. We want to use the Henderson-Hasselbalch equation, which I'm just going to write the damn equation out because I think it's shorter than writing out their dudes' names. I'm going to change HA to HX. Yeah, but we'll say log of B minus over BH. In scenario 2, so these relate to the problems that we just worked. In scenario 2, you have equivalent amounts. Equivalent moles of acid and base. So in this situation, we want to use BH concentration and Ka is equal to so these are all for like pH. Yeah, this is all for calculating the pH. So these are the 3 scenarios where you want to calculate the pH. So if you have excess strong acid, so here we want to solve for H+. For excess strong acid, we just take the pH is equal to the negative log of whatever the final HX concentration is. I'm going to get rid of these little dashes since they look like negative signs. But these 3 scenarios, and we ignore contributions. So these are the three scenarios, though, that you can end up with in a neutralization reaction. You can either have, at least for a strong acid and a weak base, I can have not enough acid to bring it to complete neutralization. In that case, I use the Henderson-Hasselbalch equation. I can have exactly the right amount of acid to neutralize the amount of weak base present. In that case, I want to use a Rice table. Specifically, I want to use the equilibrium constant with BH to solve for whatever my final proton concentration is. And the third scenario is when I have excess strong acid, and this is the simplest one. I want to figure out how much HX I have after the neutralization reaction is complete, and then I can ignore any contributions from BH, so my pH just ends up equaling the negative log of the HX concentration, the strong acid concentration. Specifically, it's the strong acid concentration after the neutralization reaction. You can't just plug in the strong acid concentration from the beginning. You have to wait until you have to consider the neutralization reaction that happens. But this is the scenario. These are all the scenarios that you can end up in for strong acids and weak bases.